this video is on section 4.4, part 4, so the final section, the final part of section 4.4, and I'm calling it the integral of a rate of change and the integral as an accumulation function. We're going to talk about how those two things are related. So first off, I want to remind you on what the fundamental theorem of calculus says. So the fundamental theorem of calculus says that the definite integral of lowercase f of x from a to b is equal to capital F of b minus capital F of a, where capital F is the antiderivative of lowercase f. Right? When we integrate lowercase f, we get capital F, and if we take the derivative of capital F, it's equal to lowercase f. So this means that we can also rewrite the fundamental theorem of calculus using different function notation. So if we thought about integrating f prime, that means that the antiderivative of f prime would just be f. And therefore, the definite integral of f prime from a to b would be just f of b minus f of a. So we're going to think about integrating rates of change. And a common rate of change, when we're thinking about a physics application, would be like movement, an object moving through space. And the rate of change of an object's position is known as velocity, right? And we'll use v of t to represent velocity. And it's common to use s. I know I've mentioned this before to you guys. It's common to use s, but like we could use x of t, we could use whatever function name we want to represent the position function, but s of t is common. So that means that s prime of t is equal to v of t. So when we integrate our velocity function v of t from a to b, that's the same as integrating s prime of t. So integrating the derivative of the position function. So then when we apply fundamental theorem of calculus, we get s of b minus s of a. And let's think about what each part of that difference represents. So s of a would be an object's position at time a. S of b would be an object's position at time b. And if we're talking about on an interval from a to b, we could think of s of b as the ending position and s of a as the starting position. So if we're calculating that difference, so ending position minus starting position, what is that going to represent? That's going to represent the distance from the starting position to the ending position, or in other words, the object's displacement. That difference we also refer to as the net change. And I know you've heard me say this before. So it's the net change in the object's position on the interval from a to b, right? We've talked about net area when we first started talking about integrating definite integrals, especially whenever a function was maybe positive and negative on an interval that we are integrating, right? We had to take into account that negative area. So when we integrate the velocity function on an interval, that ends up calculating an object's net change in position, also known as the object's displacement. So like if you thought about having a particle, let's say just moving in a horizontal line, right? And the particle is going to left or right. Left would indicate negative velocity, would indicate that the particle is moving to the left. Positive velocity would indicate that the particle is moving to the right. So if as time is passing, the particle is going to the left, and then it's going to the right, and then to the left a little bit, but not so much, and then to the right again. Whenever you integrate the velocity function that would represent that particle's movement or that particle's velocity, you would end up calculating the particle's displacement. So its distance from its starting position and to its ending position. Different than if we were talking about total distance traveled, right? Total distance traveled would be adding up the magnitude of each distance. So like taking how far the particle travels to the left plus how far the particle travels to the right plus how far the particle travels to the left again, right? And adding up all of those positive distances, right? Okay, so we're going to have an example where we're going to actually calculate displacement and then also calculate distance traveled, and it's just a little bit different. So for another example, let's integrate an acceleration function. Let's integrate acceleration. So A of t, which is the rate of change of velocity, right? A of t is equal to the derivative of velocity. V prime is equal to A of t. So if we're integrating the acceleration function, that's the same as integrating v prime, and therefore applying fundamental theorem of calculus, we get v of b minus v of a, which is equal to the net change in the object's velocity from t equals to a to t equals to b. So calculate net change in whatever you think about what the quantity is that the antiderivative represents, and it represents the net change in that quantity. So for a more generalized statement, we can look to the net change theorem. So if f prime is the rate of change of quantity f of x, then the definite integral of f prime from a to b gives the total change or the net change of f of x on the interval from a to b. Okay, so let's look at some word problems here where we're going to be calculating net change of quantity. So this one is calculator active. I have my calculator here ready. A cup of coffee at 90 degrees Celsius is put into a 20 degrees Celsius room when T is equal to 0. Okay, so then the cup of coffee will start cooling off. So if the coffee's temperature is changing at a rate given in degrees Celsius per minute by R of T equals to negative e to the negative 0.1 T, approximate the coffee's temperature after 10 minutes. Okay, so we know that the cup of coffee is initially 90 degrees Celsius. And we want to figure out after 10 minutes, what the coffee's temperature is. So we're going to take that initial temperature of 90 degrees Celsius, and we're going to figure out what the net change is. To figure out what the net change is, we're going to integrate from 0 to 10 R of T, which I'll write it out as R of T, which R of T, we are given the rule is -7. We can actually pull that -7 out front if we want. And then e to the negative 0.1 T dt. And we're using dt because the independent variable is t. You don't know how to integrate this yet by hand, but this is calculator active, so we can get an approximation of what the net change in temperature would be, temperature of the coffee in degrees Celsius, by typing this into our calculator. So -7 times math, number 9 is f int, 0 to 10, and then e to the negative 0.1, and remember we have to type in x in our calculator as our independent variable. Okay, so the approximation that I get is -44.248, and that would be degrees Celsius. Okay, that wouldn't be the temperature, right? That wouldn't be the temperature at the 10-minute mark, but that tells me that the temperature decreased by 90 degrees. So another way to write this, and we're going to talk more about this when we talk about the definite integral as in writing accumulation functions, is another way to write this would have been to say, okay, well, 90 degrees plus the net change and then you could type, here you could also write that as 90 degrees and then minus 7 times the definite integral. You could have just typed that all in. So 90, so I'm just adding 90 to that value. And we get approximately 45.752 degrees Celsius. Sorry, so the cup of coffee, maybe I should make the statement that this video is being made because we are remote with the COVID outbreak. I apologize for my cough. Okay, so this means that the coffee's temperature after 10 minutes is approximately 45.752 degrees Celsius. So this would be the actual net change in temperature from 0 to 10 minutes. And then this is the actual temperature at 10 minutes or after 10 minutes. Which is what the question was asking. Okay, next example. An automobile accelerates from rest at 1 plus 3 root t miles per hour per second. Interesting units. For 9 seconds. And I understand why, because we want to measure our time in seconds here. So, okay, the automobile accelerates from rest at 1 plus 3 root t miles per hour per second. Okay, so this is our acceleration function. This is a of t. And we want to know what is the velocity after 9 seconds. Now, it's important to recognize that it says that the automobile accelerates from rest. So it goes from velocity being 0, and then accelerates based on that acceleration function. So this is going to allow us, in order to calculate the velocity after 9 seconds, that'll be the integral from 0 to 9 of 1 plus 3 root t, not 2, dt. And this one we can integrate by hand. So applying fundamental theorem of calculus, that would be t, and then this is 3t to the 1/2. So that'll be plus 3 times 1 over 1/2 plus 1 would be 3/2. T to the 3/2. 0 to 9. Okay, and then clean that up before I apply fundamental theorem of calculus. So that'll be t plus 2t to the 3/2. So then applying fundamental theorem of calculus, that'll be 9 plus 2 times 9 to the 3/2. And then it'll be minus 0. Okay, so simplifying that a little bit just because we can. So that'll be the square root of 9 is 3, and then 3 cubed would be 27 times 2 plus 9. Will be 63. And our units are for velocity, which will be miles per hour. So the velocity after 9 seconds, and that's because it's saying after 9 seconds, so that means from 0 to 9 seconds, the change in velocity from t equals to 0 to t equals to 9 is 63 miles per hour. So this also ends up being the actual velocity at 9 seconds. Okay, so we're given a graph that represents the velocity of a particle that's moving on the x-axis. And the particle starts at x equals to 2 whenever t is at equal to 0. So at time 0, we're not given units there. So at t equals to 0, oh, we are seconds, sorry, t is in seconds. At t equals to 0 seconds, the particle is in the position at x equals to 2. And then it's going to be moving, right? Whenever the velocity function is below the x-axis, that represents the particle moving to the left and then towards the negatives. And then whenever velocity is positive, that represents the particle moving to the right. So we want to find where the particle is at the end of the trip. Where is the particle at the end of the trip? Okay, so we have to look at the graph here. And it looks like the graph is only defined from t equals to 0 to t equals 7. So I'm assuming that t equals to 7 seconds is the end of the trip. Now, if we integrate our velocity function from 0 to 7, that's going to give us the displacement of the particle. However, the particle is not starting at the origin. We are given that the particle is starting at x equals to 2. So we need to take that into account here. I'm going to call our position function x of t. So this will be the particle's position at time t, where t is in seconds. Okay, we know that x of 0 is equal to 2 based on this statement. Okay, so that means that when we go to integrate, we're going to need to take into account x of 0 being equal to 2. So the particle will end up at whatever 2 plus the integral from 0 to 7 is of v of t. Okay, so from the definite integral from 0 to 7 will represent the particle's displacement. And then we're taking into account its initial position will be at 2. Okay, in order to evaluate this definite integral, we are going to have to use some geometric formulas. Okay, so we want to calculate what this area, well, that's going to be negative area, right? And then positive area and negative area. Okay, so from 0 to 1, that triangle is going to be negative, right? Negative area, I mean. So it'll be minus, what is that, 1/2 base times height would be 2. So we're going to end up subtracting 1. And then plus, we have a trapezoid. So 1/2. This side is a length of 4. This side is a length of 1, it looks like. And then the height is 2. And then we have some more negative area. So minus 1/2 base is 2, and then height is 1. Okay, and then simplifying that, there'll be 2 minus 1. What does that? No, the 2's will cancel. So we'll have 2 minus 1 plus 5 minus 1, which is 5. Okay, so the particle will end the trip at 5. So doesn't that mean that x of 7, right? If we integrate it from 0 to 7, that means that x of 7 is equal to 5. Oh, and it looks like meters. Looks like distance is being measured in meters. Okay. So total distance traveled by the particle would be, we'd want to add up, like, for the distance or the magnitude that the particle is going to the left, and then plus the magnitude of the distance of how far the particle is traveling to the right and then to the left. Okay. Sorry. So that means that we basically want to integrate from 0 to 7 the absolute value of our velocity function. Right? We want all of our negative areas to be positive. We're going to think about reflecting them over the x-axis, okay? So this represents distance traveled. So when you integrate the absolute value of the velocity function, that will end up representing total distance traveled over whatever the interval of time is. So in this case, that will be 1 plus 5 plus 1. So 7 meters. And then I wanted to put a textbook example on here just so that you could see an example of finding displacement and total distance traveled with an equation. You'll have some of these in your practice problems. I think I'm going to do this one and then go get a drink of water and then make a second video. Okay, so we are given that velocity in feet per second of a particle moving along a line is represented by this cubic polynomial, right? This third degree polynomial, v of t, where t is time in seconds. So what is the displacement of the particle on the time interval from 1 to 5. Well, that means that we're going to be integrating v of t from 1 to 5. Okay, this is one that we could do by hand. Okay, so I should have left more space for that. That's okay. Okay, so from 1 to 5, and then applying fundamental theorem of calculus. So, because I'm running out of space, maybe I will just use my calculator here. But you would do this evaluated at 5 minus that evaluated at 1. So we should end up with 32/3. Sorry, I should be going down here. I should follow what I tell you guys to do. I'm going to draw a line here and then put equals to 32/3, and the units for distance are feet. Okay, so the displacement of the particle on the interval from 1 to 5 seconds is 32/3 feet, or 10 2/3 feet. Okay, total distance traveled. So if we think back to the example from above, distance traveled, right, we saw is the integral of the absolute value of v of t. So integrating from 1 to 5, the absolute value of v of t. Well, how do we do that? How do we integrate? Well, one option is if you have a question that's calculator active, type in the absolute value of the function into your calculator. I can easily do that here. But if this were not a calculator active problem for some reason, what you could do is you could figure out on what intervals the function is positive and just integrate those, and then also on what intervals the function is negative, so that you can take the opposite of those integrals and then add those integrals up, because we have to integrate from 1 to 5. Now, one way that we could figure out, because there's different techniques you could use. I would need to use a rational root theorem, I think, to factor this by hand. But since we are resourceful, I graphed this so that I could see what the x-intercepts are, right? So 1, 4, and 5 are the x-intercepts. And I can also, just from looking at the graph, see where our velocity function is negative and where it's positive. So it looks like from 1, okay, we're just integrating from 1 to 5. So it looks like from 1 to 4, our velocity function is already positive. So 1 to 4, it's already positive. And then it looks like from 4 to 5, it's negative. So we could take the opposite. We would want to go plus, and then take the opposite, which will just end up being minus the integral from 4 to 5. okay? Because the integral from 4 to 5 would be that negative area that we've talked about. And we want to end up adding the opposite of that value. Okay, so then it's two definite integrals. You could integrate by hand using fundamental theorem of calculus. Because this polynomial has so many terms, that would be pretty tedious. I'm just going to show you what each of those values would be. And again, you can type in the absolute value bars and just think about integrating the absolute value of your v of t function. That is also an option. Or if you wanted to type into the y equals your function and then call the function up in your integral using y bars, you could totally do that too. Especially if you know that you are going to be typing it into multiple integrals for some reason. dt dx. Okay. So did I type that in correctly? So I get 45/4, and then 4 to 5. I should have taken my own advice and typed into y equals. Okay, so then that ends up being minus negative 7/12, which ends up being 71/6. Our units will be feet for distance traveled. So again, you could type in the absolute value, or you could do this all by hand. Okay. And now I'm going to, okay, I'm back. Sorry. So I want to encourage you to pause the video right now and to read this this little blurb here that I've had written, just so that you can process it or attempt to process it on your own first, and then I'm going to talk you through it as well. So in 4.4 part 3, when we were talking about the second fundamental theorem of calculus, we talked about treating the definite integral as a function, an accumulation function, to be more specific, sorry. So in this case, where whatever capital F of x is being evaluated at, that's what gets plugged in here. And then you end up evaluating f of t on the interval from a to whatever x is, right? So that ends up being capital F of x, or f of whatever the number is that you've plugged in, minus capital F of a. That's how we can treat the definite integral as a function. Where f of a, in this case, would be equal to the integral from a to a. And you guys know that that would be equal to 0. But what if you know, or you're given in the problem, that f of a is equal to something else? Like, what if you are given a function value for capital F, or whatever the antiderivative of the function that you're integrating is. So let's say that you know that capital F of A is equal to C, where C is not equal to 0. And you want to determine what F of B is, but you know from our previous discussion that the integral from A to B of F of T would represent the net change of capital F on the interval from A to B. Where if you integrate from A to A, you get 0, not C, right? So F of, in this case, right, F of A would be equal to 0 and not C, because I'm telling you that you are given that F of A is equal to C, where C cannot be equal to 0. So we had some problems. We had a couple problems, I think, where we ran into this issue. We didn't think about setting up the integral as a function, as its own function, but we did. But we had to take into account like a starting value. The one that first comes to mind was the coffee, right? So at t equals to 0, we were given that the coffee was 90 degrees. So we had to take into account that starting temperature and then add the net change. So we need to make sure that we are taking into account what F of A is, as long as it's not equal to 0. If it's equal to 0, it doesn't matter, right? Because F, in this case, right, integrating from A to A would be just 0. And that's fine. Or you would end up doing 0 plus whatever definite integral represents your net change. So when we are trying to write what we call an accumulation function, it's in this form where you need to take into account the given information and treat whatever the given information is as your starting point. So F of A and then the lower limit of integration here should match, right? So this value for this function should be for this x value. And so that we're taking into account a starting point. In other words, we can think of the accumulation function as the amount I have now equals the amount that I started with plus the amount I've accumulated since I started. Okay, so this is a past FRQ that we're going to take a look at. It is calculator active, so I have my calculator handy, and we're going to work through it. So it looks like we are given a table here. It says the temperature of water in a tub at time t is modeled by a strictly increasing twice differentiable function w, where W of T is measured in degrees Fahrenheit and T is measured in minutes. At time T equals to 0, the temperature of the water is 55 degrees Fahrenheit. Okay. And that's reflected in the table. The water is heated for 30 minutes beginning at time T equals to 0. Okay. Values of W of T are at selected times T for the first 20 minutes are given in the table above. Okay, so use the data in the table to evaluate the definite integral from 0 to 20 of W prime of T. Using correct units, interpret the meaning of that definite integral in the context of this problem. Okay, well, W prime would be the rate at which the temperature in degrees Fahrenheit is changing with respect to time in minutes. So when we integrate from 0 to 20, that means that that's going to end up being equal, if we think about our fundamental theorem of calculus, so 0 to 20, w prime of t dt would be equal to, oh, sorry, that was 20, w of 20 minus w of 0, which is the temperature at 20 minutes minus the temperature at 0 minutes. So it's going to tell us what the change in the temperature was over those first 20 minutes. And we can see that W of 20 is 71 degrees Fahrenheit, should include the F, minus 55 degrees Fahrenheit. So 71 minus 55 is 16 degrees Fahrenheit. We need to make sure that we interpret the meaning. So we have correct units, but we need to interpret the meaning in the context of this problem. So we can say that the temperature of the water, we got a positive value for our net change. That means that the temperature of the water increased by 16 degrees Fahrenheit from t equals 0 minutes to t equals to 20 minutes, or you could say like over the first 20 minutes. The temperature of the water, to be even more specific, you could say like the temperature of water in the tub, just to make sure that, yeah, you are really answering in the context of the problem. Okay, and then question D. So we did part B of this previous free response, and we're doing part D. The other parts, maybe we don't know how to do yet, or do not relate to what we're talking about right now. Okay, so for t between 20 and 25 minutes, the function w that models the water temperature has first derivative given by w prime of t equals to 0.4 root t cosine of 0.06 t. Based on this model, what is the temperature of the water at t equals to 25? So we want to figure out what w of 25 is. We want to know the temperature in degrees Fahrenheit at t equals to 25 minutes. Okay. Well, we know what the temperature was at 20 minutes, so we could use that as our starting point. So we can say that's equal to W of 20, which is 71 degrees Fahrenheit. And then we want to know what the change in the temperature is from 20 to 25 minutes. So we could integrate from 20 to 25 W prime of t. And this is a calculator active question, so we can type this into our calculator. So in your calculator, you're going to type in 71 plus the definite integral from 20 to 25 of 0.4 times the square root of t. In your calculator, you'll type in x. Okay. You can just type in, since everything is assigned though, you can just type in or write down this statement. And then we are going based on the model, what is the temperature? Okay. So then typing that in. Make sure you are in radians. So I get approximately 73.043 degrees Fahrenheit. So the temperature of the water at T equals 25 minutes is approximately 73.043 degrees Fahrenheit. Okay. So one was just calculating the net change in temperature. The other, we were actually finding a temperature at a specific time. Okay. And another calculator active problem. This one about raw sewage. Lovely. Here, we'll use brown. Raw sewage is leaking from a storage tank at a rate given by the equation S of T equals to negative E to the square root of T, where S is measured in gallons per hour. Okay, so S is our rate, and T is measured in hours. If at T equals to 2 hours, there were 572 gallons of raw sewage in the tank. And then we're going to answer these questions. Okay. How much sewage has leaked out of the tank from T equals 2 hours to 5 hours? Okay, so we want to know how much sewage has leaked out. All right. So that means we want to calculate the net change in gallons of sewage from 2 to 5 hours. So we are going to integrate S of T. And you do not know how to integrate that yet, so you are going to type it into your calculator. We'll get our approximation. And some of these, a lot of times the calculator active ones are just so complicated, like you wouldn't be able to integrate them by hand, or it would just take a zillion years to figure out how to. Okay, so we get approximately negative 19.723 gallons. Okay, so that means that, okay, how do I want to word this? From T equals 2 hours to T equals 5 hours, approximately 19.723 gallons of sewage have leaked out of the tank. Okay, how much sewage was initially in the tank when it started leaking at t equals to 0 hours? Okay, well, in that case, we would want to figure out what the net change was okay, so we would still want to set this up as, what do I want the amount of raw? We'll use R to represent the amount of raw sewage. So, like, we're trying to figure out what R of 0 would be. We know what the R of 2 is, right? So R of 2 is 572 gallons. And then we are going to integrate from 2 to 0. From 2 to 0, because we want to know what R of 0 would be. Right? If we were setting this up in terms of T, this would be R of T, right? And this would be T or X, right? R of X. So we want to plug in 0 there. Okay, so then that's 572 plus that integral. And if we want to switch it to be from 0, you don't have to, but from 0 to 2, right? You could make that minus, and then it would cancel with that negative. U root T dt. And typing that into the calculator, since we are calculator active. Oops. Oops. All right, I got approximately 577.408 gallons of raw sewage. So there was approximately 577.408 gallons of raw sewage in the tank at t equals 0 hours. Write an integral equation that gives the amount of raw sewage in the tank. Oh, A of t. I should have looked ahead. Let's change this to be A. I already kind of talked us through this, right? So A of t will be equal to A of 2 plus the integral from, or let's say A of t, okay. To t I guess we should technically maybe change that to be an X.
just so that those variables are different. I guess if you're replacing t, I guess that's okay. It's just that we're not plugging whatever t is in right away. Here, I'm going to use x. That should be an x. So I'm going to let a of t equal to a of x. Okay, and that'll give us the amount of raw sewage in the tank at time t, or time x.